Sorted. Good morning, everyone. If you are in the Americas time, good evening if you are joining from the Asian time, I would say. We have got the pleasure today to have Jenny with us, presenting a very interesting and actual topic, CCUS in the US GOM and beyond. I will start with a little bio of Jenny, and then she will be presenting. And after that, there is a chat box where people can write the questions, and then we can have a session on Q&A. I will start saying that Jenny is the chief geoscientist at the Geoex MCG company. She's Houston-based. She's responsible for the generation of oil and gas exploration leads, focus on the American region. She received a bachelor's degree in geophysical engineering from Simón Bolívar University in Venezuela in June 2007, and her PhD in Earth Science with focus in global seismology from Rice University in December 2013. After she finished her PhD studies, she joined BP America and later Osprey Petroleum as a geophysicist before joining Geoex MCG. On a personal level, she enjoys dancing, long-distance running, cooking, and spending time with friends and her husband and daughter. So with that, I pass the baton to Jenny.
Good morning, everyone. It's a pleasure to be here with you. I would like to thank the SCG Women's Network for the kind invitation to present this project and to discuss with you this subject that is very relevant at the moment. So I'm going to talk about a project that Geoex MCG has developed recently about subsurface characterization in the Gulf of Mexico using both legacy data and machine learning. So this is just company disclaimer for very reasons. So just please refrain from taking screen captures. This presentation is going to be recorded, so you can actually be able to see it at a later time. I'm just going to briefly introduce Geoex MCG. Geoex MCG is a company that started as a multi-client seismic data provider, but now it has evolved and has different branches, hydrocarbons, hybrid 3D surveys, and recently we have also opened up to the CCUS market and natural hydrogen. For the effects of this presentation, I'm going to focus just on the CCUS section. And this is a brief agenda of the things that I'm going to discuss. I'm just going to give a brief CCUS introduction just to kind of bring everybody on the same level and to explain a few of our drivers for this project. Then I'm going to explain why did we choose the Gulf of Mexico as our pilot project. And then I'm going to actually go into the details of the project, first starting with the seismic data conditioning and then with the machine learning section of the project. So what is CCUS? This is an image that it was extracted from the most recent IPCC report, what is showing the trend of the CO2 emissions globally. And then we can also see different emission scenarios after today, what we can do. There are different technologies that we can apply to try to reduce global warming. We have solar, we have wind. However, CO2 has proven to be one of the most effective ways to try to reduce this trend. CO2 capture is not or injection rather, is not something new. Like, we have known this technology for a while, and it has been mostly used for enhanced oil recovery, in which we just get the CO2 and we actually pump it back into the subsurface to try to increase the pressure of the reservoir to extract the remaining hydrocarbons that are in place, and the CO2 remains stored in the subsurface. So we have known this technology for quite a while. This is not something that is completely brand new. Now, so how can the CO2 be stored underground? So the CO2 actually changes phases as it actually goes into the subsurface. So as we go into deeper in the subsurface, it changes to what is called a supercritical fluid. The supercritical fluid just means that the CO2, it is still dense as a liquid, but it's viscous as a gas. And the more that we pump in the subsurface, the volume is reducing. So we can actually store a bigger amount in the subsurface that we can do in the surface. In order to reach this supercritical fluid, we need to reach what is called the critical depth, which is around 800 meters. For that depth to be reached, the subsurface has to meet two criteria. One is that the temperature has to be about 31 degrees Celsius, which is equivalent at 88 degrees Fahrenheit, and the pressure had to be about 1,057 psi. Once those two conditions are met, the CO2 becomes a supercritical fluid, and we want it to remain in that stage for storage. So we have to be below that window. And the top of that window would be the bottom of that window would be the top of the overpressure, which is variable throughout the area as it depends on the geological changes. So we can apply our knowledge from the oil and gas industry into the CO2, but the CO2 storage, but the focus is slightly different. Instead of focusing on the 5 components of the petroleum system, we're going to mainly focus on 2 or 3 of those components. We're going to focus on the quality of the reservoir, the quality of the seal, and the trap. The other components, such as the source and the pathway from source to reservoir, are not really relevant for CO2 storage, as we are the ones that are actually doing or being those sources. So we need to ensure that the oil and reservoir quality are good, that we have a good porosity, and that the seal and the trap are good or are ideal confinements to keep the CO2 in place, and it doesn't escape and it doesn't go back to the surface. Which areas will be targeted first? In this map here, we have a map of the current or ongoing CCUS projects in the world. We see that the focus is mostly on the North Sea, and the US mostly onshore, but there are a few projects offshore. What do we see in common with these areas? Well, these are areas that have a very long oil and gas history. So we are very familiar with the geology of the area. There is existing infrastructure, and those and having that prior knowledge reduces the cycle of study that is necessary in order to carry on with both oil and gas studies, and also to find suitable CO2 injection sites. So why the Gulf of Mexico? So in the map here, we can observe the red outline polygon. That is the area of study. Is on the federal waters in the Gulf of Mexico, right before deep water. So we are going from the coast of, so from the Louisiana border to close to Corpus Christi in the south. This area in particular was chosen because it's where most of the refineries are located. So in the map, we see about nine refineries that are nearby, and just number 3, the Port Arthur refinery, that is accountable for 16.8 billion tons of CO2 per year. We also know that Texas is the #1 CO2 emitter in the U.S., while Louisiana actually follows second. So starting with an evaluation of the subsurface in offshore Texas seemed to be like an ideal place to try to store all the CO2 that is being emitted by these refineries along the coastline. I'm not going to go into a lot of detail on the geology from the Gulf of Mexico. This is, excuse me, just an introduction of the general setting of the Gulf of Mexico geology. This is important because this is going to provide like the geological framework that we use to determine the base of the suitability for storage. So the Gulf of Mexico is basically a two-phase rift basin, which initiated, the first phase initiated in the late Triassic and the early Jurassic. And during this period, the salt deposition followed the initial rifting. One of the most famous salt formations is that the Luan Basin, which was deposited during this time. At the end of the initial phase, the second phase started, which is characterized by the Yucatan counterclock rotation of that block into its current position. This phase ended during the early Cretaceous. These two-phase rotation basically generated a series of structures that are capable of storing oil and gas and are the setting of the prolific Gulf of Mexico. So, do we have the current lithologies for this area? Well, the yellow box represents roughly the area of study. As I mentioned before, we know that the ideal window for storage starts around 800 meters, and it ends at the top of the hot overpressure window, which is a little bit more variable and depends on the area. In terms of geology or deposition, that corresponds to the middle Miocene. So we have a study, or we have evaluated the lithology from the upper Miocene to the Pleistocene to make sure that we're encapsulating all the possible formations that could be suitable. That being said, we observe from these charts showing the lithologies that the area starts with delta-fed aprons, and then it transitions to shore zones and to delta zones. And these transgression-regression cycles generates a different set of channels from the input from the Mississippi, the Tennessee, and rivers and the Red River axis. And these provide with wood quality sands, but at the same time, it provides with shells that serves as good seals for our potential prospects. And we also observe evidence from a structural trapping, like the area exhibits predominantly normal faulting with a Listrin component, and we also have evidence of soft structures that offering potential targets for storage, as well as there have been also potential targets for oil and gas accumulation. as mentioned before, is basically within the Miocene, and there is a lot of Miocene displacement. One of the risks that we're running with this amount of faulting is that some of the faults actually can be seen on the seismic go through the surface, which might indicate that there is active movement at the moment, and those risks need to be considered at the moment of the selection of the storage sites. Those could be a problem, or those could be an opportunity. Like it's something that we need to consider during the evaluation period. So now I'm going to go into the technical section of this part, the data conditioning. So we started this project with legacy data that is available through the BOEM website. BOEM website releases seismic data that has been acquired at least for 25 years. So this data set is not a recent data set, it's at least 25 years old. And we have selected 8 3D seismic surveys that have a vintage or were acquired between 1992 and 1995. And 3 2D surveys that go from 1984 to 1990. There is a big difference between the quality of the data, the amplitude, the parameters. Like, they are very different surveys. And the area that we're trying to cover is about 31,000 square kilometers. So it's a very large area. Doing a regional interpretation with different vintage of data is usually a complicated task. So what we aim to do is to try to get a seamless transition between all the surveys without having a full reprocessing. This is also to try to shorten the time cycle. A full reprocessing from field tapes requires a lot of time, while this type of conditioning can be done in-house, and it will take considerable less time. Second, we want to apply the same method to each volume, and we want to reduce the vintage look of the data. Some of the areas will have issues. These issues will not be able to be removed, as this is just post-stack data and we don't have access to the field tapes. And so those initial problems that they were not solved during the processing will remain as part of the data set. And we have a lot of arbitrary lines that were used as QC in order to make sure that we were applying the processes correctly. So this is a summary of the workflow. We're assessing the data from the website, and then we assess for internal inconsistencies. I'm going to explain what that is in a second. We select the reference survey by comparing the wavelengths and the survey quality. We bulk scale the volumes to match the survey. We apply a MISTA analysis and time matching to just for frequency, the same with the true amplitude equalization and phase of wavelet matching. And at the end, we're going to combine, or as a way of merge all the surveys, so there are one survey throughout the whole area and not individual surveys. Again, this is just a summary of the workflow, but it's showing on the left-hand side on the right top panel. Let me see if you can pointer. In this panel here, we see one of the 2D surveys, one of the largest surveys, and this is just an RMS amplitude extraction between 1 and 4 seconds. And what we wanted to see is how the amplitude varies within the survey. So what we found is that even within the same survey, there are internal inconsistencies that needed to be corrected. So we remove the sections that they were exhibiting very different amplitude than most of the survey. And then we apply a scalar to try to match those amplitudes. And in here, we can see on the top left corner, we can see what is the result once we have balanced those amplitudes internally. Then we extract the wavelengths and the frequency spectra in order to choose the reference survey. The reference survey has been chosen to be the one that is most consistent and has the most stable frequencies throughout the whole area. That is usually consistent with the most recent survey that it was acquired, but it's not always the case. In this particular case, it was not the survey from 95, it was the survey from 93, which at the same time happened to be located at the center of the area of interest. Once we have selected the survey, we actually started to do the analysis in a radial way, comparing to or trying to tie back to that reference survey. So we start from the reference survey to each side in order to be able to complete all the surveys. And then we bulkhead each survey to match that particular reference survey. Following that, we did a mist-tie analysis just in amplitude and time to make sure that the reflectors and events were lined up. We did not allow shift more than 20 milliseconds. Most of them were around 6 and 10 milliseconds if needed. And the amplitudes were to make sure that they were balanced with respect to the reference survey in a more detailed way than the human eye can do. After we do that, we did a complete balance matching to make sure that the top and the bottom of the survey were also balanced, and not only the original window that we chose to select. After that, we focus with the frequencies with a true amplitude equalization to make sure that neither the low or high frequencies were affecting the result. And at the end, we're trying to make sure that as much as possible, all surveys were as close as zero phase as possible. I have to point out that with these volumes from the BOEM, we did not have access to the processing or acquisition reports. So a lot of assumptions needed to be made in order to make sure that all of the surveys had were consistent and had the same parameters. And at the end, we just combine them. So this is a before shot, is a line actually going through all the 8 3D surveys, and they're showing the same amplitude scale. You can see that some of them are very saturated, while some of them are the opposite, are washed out. Doing an interpretation throughout all these volumes would be very difficult if we keep the volumes on this state. And this is the after result. Even though we can still see where the transitions were, we can see that the amplitudes are more well behaved, and we can compare and do a regional interpretation throughout all volumes. Now I'm going to go through the step-by-step so you can see the difference on each step. So this is the original, or one of the original surveys. We can see that on the top, the amplitudes were very saturated, whereas the deeper section of the seismic were a little bit more dim. This is something that needed to be corrected. So the first step is to actually do the bulk gain. So in this case was a scalar of 0.167. And in this particular image, we'll also have applied the mist-tie analysis only in amplitude and time. So we see that the time shift, it was only 6.5 milliseconds, and we shift the amplitude also an additional 0.4 to make sure that it was matching the reference survey. And as I mentioned, nothing was done to the face at this stage. Then we did time gain functions at different levels in time to make sure that to remove that effect that we saw on the first image where the shallow amplitudes were very bright while the lower section amplitudes were very dim. So as you can see here, like the amplitudes on the top, the amplitude was reduced a little bit, while the ones at the bottom were increased a little bit. And a lot of art lines were actually done to ensure that the values were consistent and they were matching. Then we did a similar process with true amplitude frequency equalization. We wanted to make sure that the low frequencies and the high frequencies were balanced. In this particular example, only the middle frequencies between 20 to 40 hertz were the ones that needed to be adjusted. And this is the final result in the step where we just extracted the wavelet and applied the convolution to make sure that all volumes were as close as zero phase as possible. Now the next step, now that we have condition or seismic in our characterization criteria, is to select the wells. We started with a screening of 4,137 wells in the area in the same fashion that with the seismic. The vintage of the wells is very variable. Most of the wells are very, very old, so there is very limited data on each of the wells. So we created a selection criteria to extract the most important information, and we have good coverage, which will allow us to do further characterization and introduce the parameters into the machine learning. So the first selection criteria was the ability of digital logs. So we can see that there are not that many wells with digital logs. So we started with a selection that logs should be more than 10,000 feet to make sure that we are covering the areas of injection, but at the same time they have to be less than 10,000 feet and more than 1,640 feet to make sure that they encapsulate the regional level and the area of injection. And we wanted logs to include gamma ray, DT, ROB, and porosity. So we wanted to try to get as many digital logs as possible. The second criteria was to actually get velocity information to make sure that we can tie our seismic to our wells. Only 14 wells have some sort of velocity information, either sonic or check shot. We were lucky enough that at least for the 3D data, there was at least one well covering each of the 3D data sets. I have to point out that none of the wells had both check shots and sonic available at the same time. So it was either one or the other. And we also needed value information to make sure that we were within the areas that we wanted to be, and that we also make a regional interpretation of the area. And this is basically the entirety well log suite that was used for this study, a total of 132 wells with the different types of information. So now I'm going to dive in a little bit more into the machine learning section. The machine learning section had 3 different steps. They don't have to be exactly in this order, but for presentation purposes, the first step was the machine learning-based petrophysics and analysis of the reservoir and the overburden. The second was the automatic fall interpretation, and the third one was horizon interpretation. I'm going to start with the first step, that is the property prediction. We use a total of 70 wells with digital logs that were selected from the previous stage with gamma ray, density, DT, porosity, etc. There were about 700 miles of logs that were analyzed. And we use this data and make sure that at least it was covering the area where the 3D data is located. The workflow is basically summarized in this slide. It starts with a data review and data QC. These are potentially the steps that take the most time on the whole process. In this, the data QC here, we can see, for example, this is a density log where we have a very defined trend. However, we do have some spikes and some data that is outside the trend. So these, even though it's a semi-automatic process, is analyzed to make sure that these values are either geologically consistent or if they belong to not coupling or a bad hole measurement, they are removed from the system. Once those spikes are removed, we have a better analysis of the data. And once we have the data prepared, we move to the missing log prediction. Basically, we predict the areas or the logs that are missing. As I mentioned, this is a very old data set, and some of the logs were not missing, but they were just incomplete, where sections of the log were just not logged at the time. And some logs were just not recorded altogether. So we inputted or predicted those logs. And after that prediction is done, we can do an estimation on the lithology prediction, porosity prediction, and the saturation prediction in a way to estimate both the reservoir and seal properties. Excuse me. Going in more detail, just to show an example of a density log, we can see that in the log, all the data is confined here, and there are a few outliers in the recording. Once we remove those outliers, we have a cleaner density that has a more even distribution. And then we actually went into more detail and we actually flag for quality for with the caliper and the bit size. And we also analyzed the coupling and if it was a big hole or not, and we removed those those points that were not of good quality. And then we did run different algorithms, different machine learning algorithms, and different combinations of properties or logs to make sure that we have an accurate prediction. So this is basically the final prediction, and it was blindsided with areas where we did have data on the logs and make sure that that data was kept. The prediction did not replace the original data. The original data remained, but the original data was used as a proxy to quality and to QC the areas where the logs were missing. If the areas where data exist were good on a 95% confidence, we were sure that the rest of the prediction was correct as well, as much as possible. So this is an example of a well log before prediction. So we see that we're missing the top of the density. We're missing completely the DVTS log and feed log. So after did the prediction, we have basically a full set of complete logs that can be used for reservoir and seal characterization. And this is an example of the distribution of the potential reservoir and the potential seal. On the left, we have as a proxy for reservoir the porosity, where the yellow to red values indicate very high porosity. And in the map, we can see the areas where those are located, and we can estimate their thickness throughout the area as well. And the same is true for the potential seal, where the proxy that was used was the B shale gamma ray. So we can, using these parameters, estimate the extent and the thickness of both the reservoir and potential seal. Now we're going through the automatic fault prediction. For the fault predictions, we started with a global pre-trained model. This model was run through the 3D seismic volumes. Then it was reviewed. If the model was good, it was accepted. If the model was poor, it was reviewed and retrained, optimized, and rerun. This was done as many times as necessary in order to make sure that the selection is correct and we don't have false positive selected within the area. So here in the first image, we see what the pre-trained model is. This is the first result after using the pre-trained model. We observe that there are areas with false positive, where it's identifying faults in area where they're not. More precisely in areas where there is salt. So those were removed from a series of inlines and cross lines throughout the whole volume. The model was run again, and it was, as you can see from one step to the other, it has been refined, and at the end we have what is called the probability fault volume, what it indicates a probability that a fault is present in the area. The red is almost 100%, while the yellow is a little bit less. And this is more detail from the inline, from an inline and a time slice showing the distribution of the faults. We observe faults like this in the area that are very red, but they are in a kind of funny shape. These faults are real. It's just actually also picking up on the faults that were selected on the opposite directions. So after the fault probabilities are accepted, we can go and assign faults and extract the fault peaks from the volume and use it into a further interpretation process. Now, for the horizon prediction is basically the similar idea than the faults. The main difference is that we don't use a global model. For this, a series of experts or geoscientists have to provide the labels for the horizon interpretation. So we generated for each of the seismic volumes a label that it was 100 by 100 inline crossline. It was generated by Geoex MCG and Brazos Valley Geoservices. We basically, using that label, we run the model, and then we do a similar QC evaluation. Now that we have both the faults and bigger volume, and the model is optimized as many times as possible to ensure that these good quality. And this is basically the example. So in here we have the inline crossline labels that they were provided. And if we were to just create this this label of these seed points, we would get a surface that is representative, but it doesn't have all the details. Once we apply the machine learning, we can see that we have way more details and way more differentiation in all the structures and how that horizon varies throughout the whole area. This level of details, of course, can be generated by a normal interpreter. It just is going to be a lot faster using the machine learning than a person doing an interpretation every 2, 5, or even 1 inline and cross-line increments. Now, so to conclude, CCUS is an important part of the energy transition, so it's important that we pay attention. The Gulf of Mexico shows great potential, and it has infrastructure, and it has a good subsurface geology. Data for the federal waters is publicly available, and it can be used to do a first pass interpretation for places to store, which will reduce the carbon footprint that will be necessary by the acquisition of new seismic data. And machine learning has significantly reduced the amount of time that was necessary to do the interpretation of an area as big as this one was. And this is just an example how modern techniques can fast track the greener future. One last comment, I just want to mention that this is a workflow that we're trying to, a value chain partnership that we're trying to incorporate in our workflow. So this partnership will significantly streamline the project development for client. We will be basically on the first part of the value chain where we gather existing data, wells, condition, do the subsurface characterization, and shoot new 3D seismic if necessary, while the injection and monitoring will be done by our partner depending on the requirements that are necessary. So with that, I'm open for questions, and thank you.
Thank you so much, Jenny. It was great to see a presentation on this topic. I'm wondering if there is any questions from the attendees that they would like to share. If not, I got few. I'm going to put it here on the chat, but I will read it as well. How might advancements in related fields such as machine learning or data analytics influence future geoscience workflow in the CCUS space?
Well, for areas that are as big as this one, machine learning can actually do 2 things. One, it can speed up the process of the interpretation. Like it's not a blind or a black box where you actually just put the data and you have a result. They require human interaction, but it like every geoscientist that has done seismic interpretation know how long does it take to actually go inline by cross line and just make sure that things are picked as accurately as possible. The machine not only reduces that time, but it can also pick up things that are not necessarily obvious to the human eye. So that's one thing, that it can be more accurate, and it can show things that not necessarily are evident for us. That's basically the main thing.
Okay, I got one question related to the skill set transfer from the oil and gas to the CCS. Would you be able to share how you started and how you shift into that sector, seeing that a lot of the attendees and maybe the future attendees, they're interested on that, on the shift?
Well, technically, I have not completely shifted. I'm still kind of I'm still kind of both. Like as a chief geoscientist at Geoex, we'll still are supporting oil and gas production and exploration. That is still a very necessary part for the energy transition. We have seen multiple analysis and studies in which exploration and production is still required to try to meet at least some requirements while we actually get to finish to the energy transition. So I'm still supporting the part of the company that for oil and gas. I'm also supporting the efforts for CCUS, and as a geoscientist, the skills are very much transferable. Like it's just basically a change of focus, as I mentioned in one of the slides. Instead of just evaluating all the parts of the system, I'm focusing on 2 or 3 of them. I'm still evaluating reservoir properties. I'm still doing petrophysics. I'm still doing seismic interpretation. Like that, those skills do not change from one field to the other. Those are very much the same. What is changing is basically the mindset and the application that you use them for. So like in that sense, it has been not as a difficult transition as people might think it has been, at least not for this section of the value chain, which is the subsurface characterization. If I wanted to get more into, which we haven't done just yet, if we wanted to get more into the monitoring and future advancements, more into the engineering side, that will require a little bit more preparation and learning and modified or grab my transferable skills from one set to the next. But for subsurface characterization, the skills are very similar.
Excellent, thank you. I'm putting here another one. What are the current limitations in our understanding and technology related to CCUS geoscience workflow?
A lot of the limitations are actually based to the geology, mostly. There have been a series of ideas of possible sites for storage going from depleted fields, aquifers, salt structures, and all of them have pros and cons, basically. But you have to understand that each setting is a different setting. So if you have a depleted field, you might have also a broken silt with all the infrastructure, which can represent a path for the CO2 to escape. If you're going to aquifers, there has also been several studies that the CO2 also affects the chemistry of the aquifers and how that is going to affect the surrounding environment. And the same happened with the salts. Like even though they provide an excellent seal, they also generate a lot of faulting in the area, which can like as I heard, I think in one of the conference in the past year or so, we are not looking here for a chance of success. We're actually looking here for a chance of failure. We're trying to find all the ways in this, like how, if we put it there, how it will fail. Because that's like how soon these fail is basically how much we succeed. The longest it takes to fail, the system that takes to fail, the more successful we are.
Well, that's an interesting view.
Yeah, it's a different point of view. Like how it's basically how do I make the system fail? How do we how fast is the CO2 move in order to escape? And there are different institutions that are even doing modeling and putting some interesting models and where they put CO2 in different systems and they see how long does it take for that to get out. And that is going to also play an important role into the regulations. Like regulations in Texas are not the same as in Florida because, sorry, not Florida, California, because the tectonic setting is completely different. We have earthquakes and active faults over there, while Texas is a little bit more stable. It's more stable. So all those characteristics
plays yeah. Okay. Well, if there is no other questions, I think I'm going to stop asking. And I really thank you for your time. For
actually,
the
Adriana,
yeah,
Adriana,
yes.
there are some questions in the Q&A box.
I can't see them. Well, they are. I sent two.
Actually,
I don't know.
let me read one. There's one from Sophia.
Okay.
Is it possible to do this manually on the well prediction? She's asking about well prediction, or is it only possible to do with machine learning?
To do the well prediction manually will probably take a little bit of effort and time. We have used different algorithms and different combinations of the properties that we did have available for each well in order to predict the missing logs. And in some cases, we didn't even have enough information, so we had used models of prediction of analogs, like in this particular case, we use the North Sea in order to be able to input the wells. I guess you can always do the calculations manually. It's just going to probably take a little bit more time and effort. I do actually see the other two questions as well. So,
how did you measure the 95% confidence on parts of wells that are used to predict missing logs in other wells?
So we did blind testing on the wells where we did have data. So in those wells that we did have data, I'm going to probably get a little bit mathematical here. We use a correlation between the real data and the predicted data. And we only approved the ones that were 90% confident or 90% close to the real data. So that's basically how we did it. Like we took the real, or the parts where we did have data, as if it didn't existed, we did the prediction, and then we compare back to the real data.
Okay, and the last one is, how do they control errors in well data inputs due to normalization, data vintage, and tool types from different vendors?
Well, this was one of the parts that actually took the most time, making sure that the data was good. So that's why we use calipers and bit size as a kind of a proxy. We only use the data where the caliper was showing that it was a good hole. Otherwise, the data was just discarded. And in some cases, we started with less data than initially had, because we had to do a really deep cleanup into the basically into the data. That is a risk that you actually run with vintage data. And this was not only an issue that we faced with the well data, with digital data. We also face this issue with paleo data, where we have in the Gulf of Mexico, each operator, they do a different interpretation. So we had to normalize and calibrate and pick a standard that will actually guide our interpretation. So the well data was basically the part that took the most time, because it needed to be normalized and analyzed in order to ensure that we had quality data going into the system.
Okay. Well, I think there is no more questions. Finally, I got the box, the right box. So thank you again for your time. And yeah, I guess we will post the video on the SCG Women's Network website.
I want to make a comment. I believe that I forgot. I actually want to thank our partners from Earth Science Analytics for providing the software and the technical support to do the machine learning section of this study. That without them, this project would have not been the same. So I want to take the opportunity to thank them.
Perfect. Thank you.
No, thank you.
Yeah, very good. So everyone have a good weekend.